Yeah, welcome to the first recorded Fluids and MHD seminar of the academic year. So today we've got Ben Brown from the University of Colorado. So according to his CV that I just Googled online, some of which I knew before, some of which I didn't, he did his PhD with Yuri Tumra in Boulder, and then did postdoctoral positions at Wisconsin in Madison and at KITP in Santa Barbara, and then started in University of Colorado as an assistant professor in 2014. And today we'll be talking about approaching the solar dynamo from unusual angles, M-dwarf stars, polar views, and different dynamo mechanisms. So I'll switch my camera off now so you won't see me in the corner. Thanks.
All right. Thank you, Adrian and all. And thank you for having me today to come and visit with you. I want to tell you a couple of different stories today that are linked around the fundamental question of how do we use numerical simulations to learn about things like the sun. How are some ways that that goes wrong? And how can we learn things sort of in spite of that? Some of this is going to be some stories about M-dwarf stars, fully convective stars in the Lorentz main sequence. Some is going to be about the solar dynamo and sort of the history of our knowledge of the solar dynamo and sort of where some things have gotten with that. And a little bit is going to be about new ways we could go look at our sun to learn about fluid dynamics inside of it. I'm Ben. I'm from University of Colorado. I'm also at KITP this fall. So if any of you are coming in for the Transport and Stars program this fall, you may be able to see me there as well. Let's have some fun. But before we get into things, I want to make one thing very, very clear. I'm talking to you today because you invited me and I was able to come. And at various points in the talk, I'm going to say I, and usually when I say I, it's my opinion, and that's usually me, but I'll also say we a lot. And so I wanted to show you who some of the we is, because it really takes teams to do this work. And these are some of the students and postdocs who I've had the privilege to work with at University of Colorado, as well as my group of very close collaborators in the Daedalus collaboration. CU Boulder, we've got a grad and undergrad program. The three current students who are working with me, Whitney Powers, Imi Cresswell, and Linnea Walknowitz, are shown here. Linnea is actually on study abroad up in Edinburgh, just north of you a little bit, and Imi did her master's at Newcastle with Tammy Rogers before coming and joining us in Boulder. Jet Bordwell, Evan Anders, Ryan Diaz-Perez, Gabrielle Ortiz-Pena, Katie Manduca, and Taylor Quest, they've all finished and gone on to other positions, generally very good positions in industry, though Evan is at Sierra as a postdoc fellow, which is where Adrian and I met each other. I wanted to give you a picture that the people doing this work come from a diverse set of backgrounds, even though I'm the one who's up speaking to you today. And then there's the Daedalus collaboration. We're all old people, so we're in black and white only, because color, that's a modern innovation. We're going to start our story and our exploration by looking inside the sun. And the sun is a pretty amazing object. It's our nearest star. We have a huge amount of data on the sun, both on the surface of the sun and also in the interior of the sun. Through the science of helioseismology, we can detect sound waves at the surface of the sun through ripples in the photosphere and Doppler or brightness variations from that. We can solve an inversion problem for where those sound waves have traveled through the interior of the sun, and we can measure the interior of the sun to a high degree of precision. That means that we can constrain the internal structure of the sun very closely. We know the layout of the interior of the sun quite well. And we're actually good enough at this that we can measure Doppler shifting in the sound waves that correspond to flows which those sound waves have propagated through. At left in pink is a cartoon of the interior of the sun. The inner 5% is a region where it's hot enough and dense enough that nuclear fusion occurs. Energy is released from nuclear fusion that then trickles throughout the sun. That energy helps support the sun against its own gravity, pulling it back down in. The inner 2/3 of the sun, marked RZ here, or radiative zone, is a region where photons carry the energy. You have basically a stable stratification, and you're able to effectively conduct heat out. You do it by photons and photon diffusion, but you basically have a static, stable atmosphere in hydrostatic equilibrium. This is a region where there probably are internal gravity waves and dynamics like that, but there's no buoyantly unstable convection. You get to the outer third of the sun, marked CZ here, and that's the solar convection zone. The sun begins to convect because the plasma gets to be cold enough that it gets to be opaque enough that the photons can't get through. This drives a super adiabatic gradient, a negative entropy gradient with increasing radius, and that causes the whole system to unstably convect. When we look with helioseismology and we see the flow patterns, what we see is that there is a very large scale azimuthal or east-west flow in the sun. Red here means that it's flowing fast. Blue means that it's flowing slow. And the bottom of this picture is the equator. The upper left is the North Pole. These measurements are symmetrized about the equator, and so here they've just been collapsed into a single half of the hemisphere. Throughout the entire convection zone of the sun, the equatorial regions are red. They rotate more quickly on average than the rest of the sun. The polar regions are blue. They rotate more slowly. We call that the differential rotation. The radiative zone of the sun is solid body rotation. It all basically rotates at the same rate. The white cutout areas are spots where the inversions become unreliable. When you look in this way at the interior of the sun, you see two major shear layers, places where you go from yellow to other colors and have a lot of contours. One at the base, we call that the tachocline or speed matching layer. One at the surface, the NSSL, the near surface shear layer. Near surface shear layer occupies the outer 5% of the sun by radius. The tachocline looks comparably big here, but that's because the sound waves that are getting down there are long wavelengths. So almost like a telescope or optical observing, your view has gotten blurred down there because your wavelengths have expanded. So the view in the deep interior of the sun is blurrier than the view at the outside. We've studied the sun for quite a while. Galileo started 400 years ago. These helioseismic pictures, the first of them came out about 20 years ago of the real 2D structure of differential rotation of the sun. But despite all of that, we have really profound questions. One, why does the interior of the sun rotate like it does? Why do you have this differential rotation? Why are some of the details of this? Why are these contours tilted on radial lines? If you can see my mouse drawing on the orange contour here, why is that inclined radially rather than being straight up and down and aligned with the rotation axis like you might expect from a Taylor-Proudman theorem? And like all theorists expected until we actually saw inside the sun. Why is the inside of the sun do this? The shear layers are really interesting. Does the tachocline play a role in the global dynamo? Is a major question. This other shear layer, the near surface shear layer, turns out that's unstable to something called the magnetorotational instability. What does that even mean? And broadly, where do the global scale magnetic fields of the sun, the things that make sunspots and the things that lead to regular cyclic reversals of the solar magnetic field, where are they built? What governs their properties? We're not going to answer most of these, but I want you to get the idea of just how broad the questions still are in an object even as well studied as our sun. There's actually maybe even a more profound and kind of simpler question for the interior of the sun, and that has to do with convective structures. When we look at the surface of the sun, we see very small scale convection. We see what we call granular convection. Granular convection is about 1,000 kilometers in size, so it's about the size of France, roughly. And these cells turn over every 5 minutes. We see those really, really well. We see super granular patterns, which are a 30,000 kilometer scale, so a bit bigger. We see that through very clear velocity signatures and structure signatures. We expect from convection to see cells of convection that span the entire convection of the sun. That's 200,000 kilometers. And we don't see really any sign of them at the surface in optical measurements. Helioseismic measurements shown at the right have gotten very different results using different techniques. Something called time distance, the orange line at the bottom, that's an upper limit. So that's saying we We don't detect these things to at least this good. They have to be smaller than this if they exist. The red line here is a different inversion technique called ring diagram analysis. That says we think we have actually found it, and we think that we can put a 20% band on the amplitude of these motions. These two are 2 orders of magnitude apart, which is a lot. They use the exact same satellite data to come to these conclusions, but different inversion techniques. So there's this huge uncertainty in the observations to try and detect what should be the largest scales of motion on the fluctuating scales in the sun. We don't know how fast those motions are. And as a result, we don't know how fast the sun rotates and whether it's a high or low Rossby number object. Simulations are kind of in the ballpark of the red observations, but the disagreements between this red observation and these green and purple lines, it's factors of a couple, but that's enough to take you from a rapidly rotating low Rossby number object to a slowly rotating high Rossby number object with profound consequences for the internal flows. Okay. But to show you some of those profound consequences, I want to give you some quick history of solar dynamo models. Very broadly, in solar dynamo models, we have 2 classes of models. We have the 2D mean field models, and we have the 3D sort of quasi-DNS, LES, whatever, kind of first principles models of something. The 2D models, these ones have parameterizations for the turbulent physics. The parameterizations lead to different names. If you look into these things, you'll see there are things called like alpha omega dynamos. The alpha is the parameterization of the turbulent interactions that give the poloidal field. There are interface dynamos that live at the tachocline. There are flux transport dynamos and all sorts of variants. These 2D mean field models, they're computationally inexpensive. This means you can simulate many solar cycles. You can try lots of ideas, and you're in a position to actually try solar predictions. You're parameterizing the physics and some of the key physics underlying, but these are the most critical models for us to figure out how to use in a real sense, because they're the ones that we can use to try and predict the future of how our sun's going to behave. There's some predictions of the future in the past in the upper right corner. These are predictions from 2012 of where solar cycle 24 would get to, which we were ramping up to in 2012, and we've just finished a few years ago. There's kind of 2 classes of models shown in this figure. D1 and D2 predict a fairly small cycle with 75 or so SNSens, sunspot numbers. D3 and D4 predict the big cycle, 175 or thereabouts. After the fact, so this prediction was made in 2012, when we actually saw the peak of cycle 24, I came and put this purple band in at about where the peak is. And looking at this, you might say, well, D1 and D2 are favored. They got the right answer. D3 and D4 are rejected. They got the wrong answer. We've done hypothesis tests in some form, and we can like reject 2 of the models, keep 2 of the others, and then like move on with improving D1 and D2. Problem is that D1 and D4 are fundamentally the same model, and they have slightly different values of the underlying parameterizations of the physics that we don't understand, and they get order 1 differences. So this shows you that we really have to try and understand what these things should be from a physical perspective. What kind of model we have that can be robust to parameterization. One of our techniques for doing that is 3D models. 3D models in curved spherical geometries. These let you study global scale flows like differential rotation. These let you look at the magnetism that's built by that, and you get all the couplings from first principles in the MHD equations. These went through a lot of development over the last 20 years. I'll show you a little bit of it. They're at this phase where you can get cycles of behavior quite easily and regularly, broadly speaking. You can get buoyant magnetic structures that might be sunspot origin things. You can get a lot of interesting stuff. They're computationally expensive, and parameters for the sun are well out of reach. So you're simulating a very different object from the sun, and that has some profound consequences. I'm an expert in the 3D models. I'm much less of an expert in the 2D models. So I'll mostly tell you about the 3D models, and I'm going to focus on some work out of a particular community that I was a member of for a very long time, the ASH Anelastic Spherical Harmonic community, because that work, there's some very good things in it, and I also know where some of the flaws are, and I want to help paint a picture for you of the challenges in trying to model something like our sun. So one of the challenges in the sun is that the fluid parameters are just, they're crazy and well out of reach of simulations. The Reynolds number of the sun is probably something like 10 to the 15. We can simulate 10 to the 2, maybe 10 to the 3. Some people claim 10 to the 4, right? So no matter where we are of order 11 to 13 orders of magnitude below the Reynolds number of the sun. Either it matters tremendously or not that much at all. And we're still trying to figure that out. It might not matter that much at all if you can capture a class of like consistent scaling turbulent behavior and be in the turbulent regime. That's sort of the big dream that physics saves you. The Ekman number of the sun is about 10 to the minus 15. That's very similar to the core of the Earth. The big difference between the sun and the Earth is that the sun is a magnetic Prandtl number like 10 to the minus 2, 10 to the minus 1, rather than like 10 to the minus 5, 10 to the minus 6. So it's very turbulent, very magnetically turbulent. Thermally, the thermal Prandtl number is pretty small because radiation is really good at transporting things. The Rossby number of the sun, we've thought for a long time was about 1. It may actually be a fair bit smaller. We don't really know. We don't have direct observations of the deep motions. The history of solar dynamo models goes back quite a ways, back in fact to before I was born. In the early 1980s, when I was born, Peter Gilman and Gary Glatzmeyer were working on the first 3D spherical global solar dynamo models. They did Boussinesq models early on, but by 1985, they had anelastic models with anelastic MHD dynamos. Boussinesq, you all know, anelastic, if anyone hasn't encountered it, is a like stratified analog to Boussinesq, is one of my ways of thinking about it. You capture large scale density stratifications, but still have very subsonic flows. In the 80s, resolutions were low, dynamics were limited. The differential rotation you got out was solar-like. The black and white image here is the differential rotation from Gary Glatzmeyer's 1985 work. Solid lines, prograde, so red in the right, dotted lines, retrograde, blue in the left. We didn't know the geometry of the solar convection zone when Gary was doing this work. So this is a thicker solar convection zone than the real one. We didn't even have helioseismology when he was doing this. And he was getting something that's not wrong. Okay, continuing in history, in the 2000s, there'd been a lot of advances in computing, and Yuri Tumre led a rebuilding of anelastic spherical codes for these modern computers. And this led to something called the ASH mob. Here's a picture of all of us in probably 2006 or 2007, thereabouts. There are many people who you may have come across the names of if you've been in stellar astrophysical fluid dynamics. Yuri Tumre, as our eminent leader, is wearing the bunny ears. Sascha Brun, right here of CEA Saclay, is here in a suit jacket because he's French, so he actually dresses professionally rather than like the rest of us slobs. I'm holding a giant teddy bear back when I had shorter hair and no beard. This is Mark DeRosa from Lockheed Martin. This is Matt Browning, who's now at Exeter. Nick Featherstone, who went on to develop the large-scale open source Rayleigh code for dynamos and fluid dynamics in spheres and boxes, and Kyle Augustin, who has done a lot of work, especially in sort of fundamental physics of stars. For quite a while, there was a lot of progress. ASH simulations really took off with the computing resources that were available. Dynamos were being achieved in like 2004. There were attempts to do detailed matching of the solar differential rotation guided by thermal wind theory from Matthias Rempel and effects in the tachocline printing through the convection zone. This thing AB3 in the middle was one of their simulations, and I show the solar differential rotation at the right. And like now they've got a red equator, they've got things tilted over on radial lines, like it's very nice. Resolutions were kind of middling. Time evolution was longish. The picture at the left is the sphere unwrapped and the radial velocity patterns, and this is pretty laminar, but the results are pretty promising. 2006. Bigger computers meant bigger sims. By 2008, that was kind of a high point of these things, sort of 1,000 cube level, 680 spherical harmonic degrees. The dynamics are much prettier. So same kind of picture at the left here of the radial velocities in an unwrapped weighty. The equators at the middle, the poles are at the top and bottom. Very beautiful. The differential rotation's not looking nearly as good now. This is, it's still red at the equator, it's still blue at the poles, but it's gotten a lot rattier. It doesn't look anything like this. So the differential rotation has kind of degraded as we've gotten more turbulent here. What was happening, what we figured out later was we were trying to simulate the sun. So we were dialing a solar luminosity dimensionally, a solar rotation rate dimensionally, and then we were putting in various other constants like viscosities at vastly inflated values. And while we walked on a path in parameter space, we were changing the Rossby number of the sun in ways we didn't understand. We'll come back to that in a moment. A whole bunch of grad students got started out of Yuri's group, started studying other stars. This has led to a lot of people who are actively participating in stellar astrophysical dynamics through the present. Lorraine Jouve I think she's in Toulouse, and apologies if I get that wrong. Lorraine is still very active in the field, did a lot of work on Babcock-Layton dynamos and flux ropes. I'm a professor at Colorado. Matt Browning's a professor at University of Exeter. Nick Featherstone's very active in the field. Nick Nelson's a professor in the California State University system at Chico. There's a bit of an industry. We learned a lot of things. We studied a whole bunch of different stars. Some of the things we learned are still true. And some things we found out we weren't studying quite what we thought we were. When you look across the entire main sequence of stars, so stars, when you look out in the universe, generally their properties change as their masses change. Small stars are very red and very cool. Big stars are very blue and very hot. This diagram here in black is a Hertzsprung-Russell diagram, which is an astronomer diagram for categorizing stars. Luminosity, brightness vertically, surface temperature, and hence the color of these objects horizontally. And all of the stars that are in kind of the normal part of their lives lie in what we call the main sequence, this diagonal line here. Matt Browning did M-dwarf models down at the lower end. Sean Matt, now also at Exeter, did a bunch of different types of stars in between. Kyle Augustin did higher mass stars. And, you know, we had various meetings. We talked a lot. We thought we were learning things. This is a picture of me in 2013 with this exact same diagram. We had a large theoretical collaboration that spanned multiple universities to try and understand and use these for figuring out stellar dynamos. One of the things that we found that I think holds up pretty well is that the differential rotation of these objects, the large scale flows, over a whole bunch of these different kinds of objects is well predicted by the dynamical Rossby number in these objects. If you know something like how much vorticity there is in your flow compared to the planetary vorticity, 2 times omega naught, you can place simulations on a curve, which is the white box kind of at lower middle, and the simulations all kind of fall on that curve. The horizontal bit's that dynamical Rossby number. The vertical bit is how much differential rotation there, and in a signed fashion. So all of these are positive. There's a maximum around, say, 30 or so %, which is about what the sun has. When you go to lower Rossby numbers, you get less differential rotation contrast, but you still have lots of shear. As you go to higher Rossby numbers, you get less differential rotation contrast, and the shear starts to fall away. And they all look broadly similar. Even this fully convective M dwarfs, which I'll show you a little bit later, different color bar than the rainbow color bars the other, but exactly the same behavior, and it's this little M that's right here. So follows all the same sorts of things. These were built at the time off of what are called stellar structure models, which are large, complicated solutions to hydrostatic, thermal, and chemical equilibrium in stars. And they are a tool for trying to guess the 1D structure of stars. Some of those, like at the sun, we know are correct to within a few percent or less. For other stars, some of them we can measure. We don't have the same level of constraints, but it's a pretty mature industry with some major outstanding problems too. Well, we thought at the time that the stellar structure models were a crucial ingredient to get in there. And I think another big takeaway from these things is that by going especially to lower Rossby number unit areas and to lots of different types of stars, we found that MHD simulations, at least, of these sorts of stars, you can create large-scale magnetic fields in the middle of the convection zone of the stars. You can have a large-scale organized field generation in the middle of the churning convection that's building it. And that means that there's no interface that this is relying on. There's no tachocline stable layer or other sort of gross properties like that to enable organization and large-scale field. It can naturally arise out of rotational correlations and the differential rotation. Shown in the movie is a cutaway of one of these 3D simulations. The lines are magnetic field lines that have been traced through the volume in a visualization. The colors are a polarity. And the movie starts out with red at the top at the northern hemisphere and blue at the bottom at the southern hemisphere. And then over time, we get into a reverse state here. We now have blue at the top and red at the bottom. So this thing is cycling. It has some hemispheric symmetry. It has some repeatability in time. It does lots of interesting things. Okay. These things cycle at a fundamental level. We don't know why they cycle. Right? When you get a large 3D numerical simulation that does something, it can be as complex as an actual physical object and observation. So we can observe that these things cycle, but we don't understand the physics at a level where we can write down the cartoon level, like, yes, here is why they cycle. Here's the fundamental physics of this. We have ideas, but none of those have been rigorously tested yet. Lots of work in this space to do. Kind of takeaways and things that I think hold up from that early work on global scale dynamos. Shellular dynamos, things with a shell geometry. There are lots of solutions with globally organized fields. They generally show up at moderate to low values of the Rossby number, and you get them whether or not you have a stably stratified radiative zone and tachocline underneath for some value of tachocline and radiative zone. There's some really interesting questions. One is, what's the Rossby number of the sun? The sun does organize magnetic fields and reversals. We've thought the solar Rossby number was 1. Is it actually something small? Is it like 0.3 or 0.5 or somewhere in that range? Is it 2 to 3 times smaller than what we had thought? A corollary, if tachoclines don't matter, well, these are shellular dynamos and there's an inner boundary condition, and maybe that's still acting like a tachocline. So what if you just got rid of the tachocline entirely? Could you show that you get organized magnetic fields without a boundary condition creating the symmetries that lead to this? If the tachocline's not doing anything, if that shear layer is not important, what about the other one, the near surface shear layer? And like, fundamentally, what are we modeling in the first place? What are these objects? Are these really stars, or are they something else? And this last question, this brings us to a real error that happens in modeling. In numerical simulations, you can have errors that come from all kinds of things. You can have numerical errors from resolution or time stepping. Those are pathological, but we have some tools to catch them. You can have errors of approximation, right? Where you say something like, yeah, the real dynamics is compressible, but I'm going to use a Boussinesq approximation to study this thing and simplify the physics and try and understand it. Or I'm going to do a 2D model rather than a 3D model. Like those are a fundamental choice. The choice might be a good choice or a bad choice, but it's a choice of the approach. The other really big error I think we make, especially in astrophysics, is what I would call errors of application. This is where we've like sorted through the numerical stability errors, and we've sorted through the choice errors. But now we say something like, well, we're going to try and do a model of something like the sun. And we think that the right way to do it is to say fix the luminosity, the rotation rate, and the mass, and let other parameters be free, like viscosities, things like that. And I would argue that that's an error of application. That's a not understanding the non-dimensional parameters that govern the object that you're trying to study, and not understanding the non-dimensional parameters that you're actually setting in your simulation. And it's a very easy error to make, and one that I spent quite a lot of time making at various points. And in particular, an illustration of that is right here. Here are 3 different kinds of stars that I was simulating at one point, as well as some results from Kyle Augustin's simulations. These stars range from about 1/2 of a solar mass to 1.5 solar masses. Their luminosities change by more than an order of magnitude over that span. Their convection zone geometries go from being 1/2 of the star at the low mass to about 1/10 of the star at the high mass. If I cover up the color bars of these things, it's actually basically impossible to tell that these are different simulations. And that's because each of these simulations is running at similar non-dimensional parameters for the Ekman number and really the dynamical Rossby number. So these are actually, like, very arguably, these are simulations of the exact same object. Really, the only thing that's changed here is the geometry, but these have generally all had the same amount of density stratification, so it's not even clear that the geometric effects are being felt by the dynamics with any strength. The actual stars, the lowest mass ones in the upper right, the next is at the upper left, star like the sun's at the lower left, and the more massive stars at the lower right. And if I shuffled these and covered up the color bars, you wouldn't be able to unshuffle them or tell which was which, especially if they didn't have, if they were all visualized at the same depth in the simulation. So that's an indication that you have to be very careful when you're using dimensional values to set simulations. You have to be very careful when you're using non-dimensional values to map them back onto real simulations. You just have to be careful where and how you apply simulations. A related story in the sun is that as we made our simulations more and more turbulent, we ended up in a very different state than we expected. So while fixing these parameters, luminosity, mass, radius of the sun, the things that we can measure directly, and changing the things that you might hope don't matter as much, the thermal diffusion and the viscosity, you can drive this. So when you're changing those viscosities and thermal diffusions, right, you're changing the non-dimensional parameters that actually govern the simulation. You're changing the Ekman number, you're changing the Rayleigh number, and you can drive the simulation at same like gross physical parameters. But with a small change, you can drive it into a very different basin. And here's one of these. This is what we call an anti-solar differential rotation. So this is a solar simulation of the solar luminosity, a solar rotation rate, yada, yada, yada. Differential rotation profile is shown here at middle. It's blue now at the equator rather than red, and the red is now at the poles. So the poles go around really fast. The equator goes around retrograde compared to the overall frame rotation. So the shear has flipped, and it's an extremely robust result. Here are the convective patterns. They don't look markedly different. To one skilled in the art, you can see that the cells are a bit less aligned with the rotation axis, and they're a bit more kind of breaking up like kind of granulation, so they're less rotationally constrained. So you can see by eye that it's a higher Rossby number solution. And if you if you sweep in a dimensional parameter space at one set of values, the solar-like things live in the upper right of the parameter space, and anti-solar things exist in the lower left of the parameter space. And the sun is like down and to the left by like several feet on a log scale. The scale here is the physical diffusion values in a simulation as done at that time. And these are values of like 10 to the 12, and the values in the sun are like 10. So the sun's well down into the left, and any attempts to go down to the left completely change the character of the solution to something that's obviously not the same as the sun. And I would argue that the solar community actually got real lucky here, because we walked on a pathway that seemed a reasonable pathway to walk on. We got an order 1 disagreement with the observations that we have on hand, and that's the kind of disagreement you can't just sweep under the rug. That's a kind of disagreement that causes you to really pause and think about what your problem is, and how to do better at simulating it. Our problem here was that we thought we were simulating the sun. We weren't. We got the non-dimensional parameters wrong. We got the Rossby number of the sun wrong in particular. Okay, so what can we do? Well, I'm going to show you some like hopeful things going forward, but I want you to remember, as you probably know, coming from applied math trainings and backgrounds, simulations, they're a thing unto themselves, a tool unto themselves, and they're not generally something, especially in astrophysical situations, where I think you should try and simulate a particular object in detail and think that you're going to be getting that object per se. They're really a place to test ideas. They're a place to make us stop and think about the ideas we already have, and to suggest new experiments or new ideas about the ways things might be working that we can then go and confirm. They become very powerful when you have suites of simulations and you can explore changes in a property along some axis in the parameter space in the non-dimensional control parameters. Okay. In our group at Boulder, we've been doing a lot of that, partly because of sort of seeing where the global solar dynamo was going to and realizing that we didn't know how to get out of it. We spent a number of years focusing on detailed physical problems that we could kind of isolate and test. Evan Anders was one of my students. He did a portion of this work. He did some neat experiments showing that like stratified compressible convection transports heat in a way much like incompressible Rayleigh-Benard convection. And you can use the language of Rayleigh-Benard, and you can use a Nusselt number, and you can get very similar scalings out of even high Mach number compressible convection. Jack Bordwell did a lot of work on chemical mixing, and showed ways to take 2 and 3D models of chemical mixing by convection and turn them into 1D parameterized theories that are different than mixing length and do a better job than mixing length. We found out that rotating convection, that you can actually control the posteriori Rossby number by setting your non-dimensional parameters in the right ratio, using something that's basically the convective Rossby number, and we're able to test that in stratified settings and show that it works very well, show how that works between boundary convection versus internally heated convection. And we also found ways to do things like accelerate long, slow evolution of things like thermal evolution by running simulations, creating statistics out of them, and then trying to guess forward where they would go to. We did some real science too. We tried to hypothesis test work done by other scientists, and we tried real hard to show that they were wrong, and we failed to do so. And so we failed to reject our hypotheses, which is like what you're always taught to do. And then I think that's one of the first times I've ever really conclusively done that in my career. A lot of fun. Those were all box geometries, Cartesian geometries, focus studies. And I want to talk a little bit now about pairing Cartesian geometries with global simulations and ways we can use even old simulations. This is the one I was showing you from 2008 to make us try and think about new ways of looking at the sun and new ways of solving problems. So I'm going to show you 3 things quickly. We're going to start with hunting giant cells at the solar poles. So the big question is, what is the Rossby number in the interior of the sun? And can we see the giant cells of convection that span the convection zone to try and figure out what that Rossby number is, both observationally and theoretically? What do we know about solar convection? Well, like I said earlier, we can observe the surface really well. And the surface flows are small scale and not rotationally constrained. The sun rotates once a month, roughly. The convective patterns that are playing in the background here, as imaged by the DKIST solar telescope, the Daniel K. Inouye solar telescope on Haleakala in Hawaii, these have 5-minute time scales. 5 minutes is much less than a month. And so these don't know anything about rotation. We see these super well. These are almost all that we conclusively see. The thing that's missing when we try and take those and apply them to our understanding of the deep interior is rotation, right? Those do not feel rotation. They feel stratification. They feel other things. And what happens when you add rotation? Well, when you add rotation, you add a constraint to the system. This leads to fundamental changes in things like your convective structures. Your convective structures tend to align along the rotation axis, and they tend to swirl and have high vorticity rather than being spreading, diverging centers that then collapse on themselves. At left is some work by Evan Anders in Cartesian boxes. These are different simulations at basically the same Reynolds numbers, so same amounts of turbulence, same amounts of scales present in the problem, but different Rossby numbers. Upper left, low Rossby number, pretty unorganized flows. Lower right, very low Rossby number, highly organized flows. So strong rotational constraint at the lower right, weak rotational constraint at the upper left. You can kind of see just in this little movie that as you go from upper left to lower right, you get some pretty substantial changes in the character and the structures. All these are running on the same time scales, and that time scale has to do with the dynamical time. And so you're seeing things evolve quickly in the upper left because the dynamical time to rotation is fast. And in the lower right, you're seeing things evolve slowly. The rotation has really caused these things to stay coherent for many, many more dynamical times. All right. At the same time that, and there's been a lot of, the rotating convection literature is huge and deep. And there's a huge amount of work out there by a huge number of teams, and some really neat stuff's been coming out in the last decade. Some of that's come out very, very recently is taking sort of models of rotating dynamics, taking those back to the stellar structure models and trying to come up with better estimates of the Rossby number of the interior of the sun based on simple parameterized convection models informed by rotation as well. Jeff Fassel, Keith Julian, and Nick Featherstone have a very interesting PNAS paper from this year where they go and do these calculations. They find that the Rossby numbers in the interior of the sun are kind of middling small. And the big surprises, so the solid lines are their results, the dashed lines are sort of classic results. The big surprise is that the convective scale in the deep interior of the sun might be 30,000 kilometers rather than hundreds of thousands of kilometers. So this red line is showing you the effectively column scale of the rotationally constrained convection in the deep interior rather than the sort of spreading center scale of diverging classical convection. In a cartoon view, right, non-rotating convection, the picture many of us have in our head for the interior of the sun's rotation looks like at the left, you get sort of large eddies that range from small scale at a boundary to filling the entire convection zone in the bulk. That's the blue lines. And at the right is our cartoon view of a rotating sun. You still get small eddies at the upper boundary where rotational constraints are broken by the very short time scales. But the deep interior where you're rotationally constrained, you now have kilometer structures. Those are going to print up to the poles very differently than they show up at the equator. And you're going to have swirling vertical patterns where they print through at the poles. Something like this is maybe more like reality, with a characteristic diameter scale or radius scale of like 30,000 kilometers. The depth of this thing is 200,000 kilometers. So there are like 7 of these across the convection zone of the sun if you stack them up at the equator. All right. So, okay, so there's a lot there to test in simulations, but there's some of this that can be tested by observations if we got a different viewpoint on the sun. We observe the sun from the equator of the sun because we orbit in the ecliptic, and the planets and the sun all share the same angular momentum from their birth. And so the Earth orbits around at the equator of the sun. So that's our vantage point. An equatorial vantage point on a rotating object like the sun is challenging. It rotates once a month, and that means that any region you see on the sphere sweeps out of view roughly every 8 days. And you never see the whole equatorial region all at once from the same instrument. The only ways around that are to fly lots of satellites around the sun at 1 AU and try and get images from multiple vantage points simultaneously. We've done a little bit of that with the stereo missions 15 or so years ago, but we don't have good assets for observing the sun all the way around it. A really fascinating vantage point on any rotating object is to get a view on the poles. And a polar view of the sun, I think, is one of the most interesting things we can observationally go and try and get. Here, the polar cells come up to the surface. Here, you would see them swirling rather than spreading and diverging. I mean, if you get a high enough vantage point above 45 degrees north, especially if you're up at like 60 or 70 degrees north, you actually could keep the cells in view as the sun rotates underneath you, because your field of view covers the entire tangent cylinder portion of the sun. The tangent cylinder is at about 45 degrees north, so you have to be higher up than that to see the whole tangent cylinder. There is a proposal for a mission to do this. It's called the Solaris mission. If the Solaris mission flies, it will end up having about a 3-month view above the North Pole and a 3-month view over the South Pole on its orbits, on its first orbit through. That's 3 rotation periods. The surface patterns you need to average down on range in timescales from 5 minutes to a day. So that means you can increase the signal to noise on the underlying giant cells of convection by factors of 10 to 100 or more. So there's a real chance that you could actually see the giant cells if they are there and if they remain coherent over these timescales. And they would do that if they have low Rossby numbers. So if giant cells of convection are indeed relatively low Rossby number, observational views from flying over the poles of the sun might actually show you those. And there's a real chance that we have those observations within the next decade or so. And that'd be very exciting. Let's talk about something. Oops. Just gestured and knocked my mic out of my ear too vigorously. Let's talk about a different thing. Let's talk about a thought experiment problem. What happens if we remove the tachocline, the lower boundary layer, entirely? What if we get rid of that boundary? Do dynamos still work in the ways that were being found for cellular dynamos previously? That's an interesting thought experiment. And we're going to do it in a particular star that actually has the physical property of not having a tachocline. At the bottom of the main sequence are the M dwarf stars. When you get these small enough in size, they become fully convective. They convect from their nuclear burning cores all the way to their surfaces. Astronomers are super interested in them. They're super magnetically active. They're much more active than our sun. They are the most numerous stars in the universe by no small amount, and they're the host stars of most of the planets and possibly most of the habitable planets in our universe. So astronomers care about them a whole bunch. They are where we found Earth-sized planets around. They're very interesting stars. Our nearest star, Proxima Centauri, is an M dwarf star, and it probably has an Earth-sized planet around it. Now, the problem is that they also have giant magnetic flares, and so they may not be habitable. They may be habitable from a planet position perspective, but not from a stellar activity perspective. So they're interesting to try and understand their dynamos a bit. They're also interesting from a fluids perspective. They're really simple objects. They're, from a fluids perspective, they're a low Mach number, fully convective object that has non-constant coefficients that are pretty simple. The density and the gravity and things like that we care about, those are basically Lane-Emden solutions, which are the classical polytropic solutions to a self-gravitating sphere. You can do them analytically, you can do them numerically. They're very, very simple. They're probably the simplest solutions to do in a sphere. They have an internal heating source. We take that from stellar structure models, so it has like the right shape from stellar structure models. It's a mix of nuclear generation and internal radiative transport. It basically has a peak at the core and distributed heating everywhere else. It kind of looks like a Gaussian plus a constant or something like that. And you can come up with a source model that matches the stellar structure heating functions pretty simply. That makes them pretty straightforward to simulate if you have a tool that can simulate your equations in your geometry. And in the Daedalus collaboration, we've spent a lot of time developing tools for simulating fluids problems and other PDEs. And over the last year and a half, we've been working particularly hard on a new open source, publicly available spherical simulation framework that can capture all the way through to the R=0 singularity in a ball. So it can do Cartesian boxes, it can do spherical shells, it can do disk geometries that go into R=0, and it can do ball geometries that go into R=0. The stuff I'm showing you here, this is anelastic MHD equations. They're spectrally accurate. Our big thing in Daedalus is that the equations are something that can be readily changed around by the user. And here's some work that's a convecting simulation. The movie at the middle is showing convective plumes. It's got a Reynolds number of like 100 or so and a Rossby number of like 0.3. Makes a differential rotation that looks a little bit like the solar ones we were seeing earlier. It also builds large-scale magnetic fields throughout the interior of this object. It builds a distributed convection zone dynamo, much like the cellular simulations we're doing. It has some differences. The really fascinating difference is that it builds that convection zone dynamo entirely in one hemisphere or the other. And it, like, the top is a map in time of the magnetic field. Sometimes it's in the southern hemisphere. A lot of the time here it's in the northern hemisphere. It cycles in the northern hemisphere. It does all sorts of interesting things, but the bulk of the magnetism in this simulation is in the northern hemisphere. And you can learn lots of interesting things from this. I think the most interesting thing is that you can organize global scale magnetic fields without having a tachocline of any kind, either a internal boundary layer or a just like boundary condition. If you remove both of those, you still get globally the same kind of behaviors. So what we're seeing in these is some sort of interaction between an unknown bulk process that builds a poloidal field, or alpha-like effect, whatever that is, and a large-scale differential rotation that builds the toroidal field from that. And these simulations are simple enough, we might actually be able to pick out that poloidal field process. Okay. I'll tell you 30 seconds about one exciting thing, and then we're going to wrap. The other exciting thing that's sort of like crazy ideas for the future, the sun has two shear layers in radius. It's got the tachocline, which I just made a case for may not play that much of a role in the solar dynamo. What about the near surface shear layer at the top? When you look at differential rotation profiles of the sun, the tachocline draws the eye, but the near surface shear layer may be more interesting. It's a region of as much or more shear, and the shear is declining as you go out in radius. As you go out in radius, it goes from being fast to somewhat slower, and that ends up actually being ripe for the magnetorotational instability. So the diagram at the right is a gradient of the differential rotation weighted in a particular way. And the red regions are those regions that have a negative gradient and that are potentially MRI unstable. Now, trying to understand MRI instabilities in the near surface shear layer is complicated. The near surface shear layer itself has a radiative boundary layer, so you probably need some degree of radiative MHD. Maybe not, but you might want to at least check things there. You need global geometries so that you can capture changes in shear with latitude, and also the connectivity for the global dynamo. And we think that these are probably essentially nonlinear dynamos, a little bit like work that Nick Brummel and lots of others did. I think Steve Tobias probably did some of that work with Nick, but Steve will be able to either affirm that or correct me when we're visiting in a little bit. These are probably essentially nonlinear states, so you may not be able to get them from seed perturbation. So you may have to use adjoint methods and other techniques to like get a solution and then walk it back to parameters. And we have some ideas on how to do that. We have some ideas of how to do that. We also have a major NASA award that Daniel Le-Koné got out of Northwestern University that is funding studies of magnetorotational instabilities in the sun and whether or not those can be running effectively a MRI instability dynamo. All right, I want to leave you with some parting thoughts, an analogy with boats about simulations and what we can do really well. This is 4/5 of the Daedalus core collaboration in a boat, sailing around in Boston on a very calm river. We're in a nice little 14-foot dinghy. I'm at the tiller right now, and I haven't currently flipped us. Here's Keaton Burns, Jeff Oishi, and Daniel Le-Koné. We are sailing back and forth and having a grand old time. And we're relatively competent at doing this under these conditions. There's not very much wind. There are bridges on either side of the river, keeping big boats away from us. And we're like going back and forth on this little stretch of river. We're doing great. No one has fallen in the river at all. Everyone's having a good time and dry. Here's what we often think that we can do. And now our boat has changed a little bit. This is an America's Cup boat designed for sailing across the Atlantic and the Pacific. This particular one, hydrofoils. This is the Team New Zealand boat. So the gentlemen on the rail here are New Zealand All Black rugby players. They have a physical prowess that is like at the peak of what human beings can do. And they are all just barely keeping this boat together and racing as fast as you can possibly do. And in like a simulation kind of perspective, we're like, oh yeah, we can totally do this really big, complicated thing, like simulate the sun itself for you. Boats like this have different instability modes than simple boats. Here's what often happens when you push them to their limits. And the thing in simulations is that when we push them to similar limits, we don't always know that we wrecked ourselves to the same degree. Here, the boat's flipped upside down. It's unambiguous. For us, when we got the wrong solar differential rotation profile, it was again unambiguous. But sometimes we get solutions that we think are fine, and we don't know that we've just basically completely wrecked them because we've wandered into the wrong parts of parameter space. It takes a lot of humility, and it takes a lot of careful experiments to try and figure out whether or not the simulations you've gotten actually have predictive power and the ability to help you understand the universe that we're in. I'll leave you with some final parting thoughts. I think it's incredibly important that we have open source tools and that we also have open source publication of the implementations of those tools. That's because reproducing numerical work is a very, very, very hard. And this really cripples what we can do as scientists. In astrophysics in particular, the standards are particularly lax, I feel. It's very easy to publish work that is essentially non-reproducible. It's lacking critical details or things like that. It's very important that we figure that out for the sake of the science we're trying to do. Open source tools help ease the barrier to entry. You need to have the implementations too. Like I can show you an M-Dwarf dynamo simulation, but if you have to go out and build your own, even using our Daedalus tool, we know lots of things about how to do things right and wrong. We need to convey that expertise and knowledge to you so that you don't have to start from the ground up. Lastly, open source community tools can be built and maintained relatively cheaply. The whole Daedalus project over its 7-year lifetime has probably cost something like $2 million. That's through prize postdocs, volunteering labor, that's through funding from faculty members who've started at universities, that's from a few different sources. That $2 million is probably in the right ballpark. Other major code projects like the Flash code out of University of Chicago, that was north of $100 million. At $2 million, there are downsides. There's no dedicated support staff and phone line you can call. The Flash Center did have those things. But you can still also build a very large community tool on the cheap and get a lot of people doing science in very interesting ways, and ways that we did not ourselves predict when we built the tool. With that, I'll stop talking. I'll leave the slides up for the moment. I've gone 5 minutes over, and I thank you all for coming to our talk, and I'll take questions and stay for as long as people would like to visit.
Thanks, Ben. Nice talk. So I'll just stop the recording now so people feel free to ask questions.